Okay. 3 topics today. Topic 1, still QR factorization. Still QR algorithm. This algorithm find all the eigenvalues of a matrix simultaneously. In practice, this algorithm is not perfect. Actually, it has many computational problems. In second topic, I present some improvements on this algorithm. If I still have time, then we turn to section 4 about iterative methods for the solution of linear systems. Here is the QR algorithm. This algorithm is simple. In each step, perform QR factorization of matrix, say AK. Then after we get the QR factorization, multiply the 2 factors Q and R in reverse order to get a new matrix. Then repeat this 2 steps. Yeah, this step and this step, these 2 steps again and again. It can be proved under some conditions. Under some conditions, it can be proved the iterate AK SK is increasing, then AK will approach some upper triangular matrix. Then upper triangular matrix is eigenvalues are just the entries along the main diagonal line. So we can read the eigenvalues of the original matrix from the main diagonal line of this upper triangular matrix. Yeah. It is easy to see that all the iterates AK plus 1, they have exactly the same eigenvalues because AK and AK plus 1 are similar matrices. Let me show you one example about this algorithm. Okay, take a look at one simple example. Consider this matrix 2 by 2. Okay, yeah, 2 by 2 matrix. Yeah. Then perform the QR algorithm on this matrix. The exact eigenvalues is eigenvalues are 4 and 1. Okay, then I perform QR algorithm on this matrix to get 4 and 1. Okay, to get 4 and 1. Okay, now solution. Step 1, set A0 to be A. Then perform QR factorization on A0. Yeah, QR factorization. The matrix Q is 0.7071. All numbers are 7071. R0 is upper triangular.
你要吃了什么不？
Yeah, please mute. Okay, please
我的
mute.
院子里去了。
Okay, now form the matrix A1. A1 is R0 times Q0. It is 4, 0, 1, 1. Then perform QR factorization on A1. We get Q1 is 25. R1 upper triangular. Yeah. Then form the matrix A2. A2 is R1 times Q1. The matrix is a 4.5 AA 0 7674. No, 0.2 353. Yeah. This is K is 2. Okay, and so on. Then factor this matrix into Q2 and R2. After 9 iterations, then we get we have A9. Then perform QR factorization on A9. This is 9. Okay. Q9, R9. R9. Okay. Let me move this up. Okay. What is Q? Q9 is identity matrix. R9 is 4, negative 1, 0, 1. Then form the matrix A10. A10 now is R9, Q9. Q is identity matrix. So 4, negative 1, 0, 1. So after 10 iterations of the QR algorithm, we get A10. A10 upper triangular, and upper triangular is eigenvalues 4 and 1. Yeah, exactly. Yeah, the exact eigenvalue of this matrix is 4 and 1. Yeah, after 10 iterations, then we get 4 and 1. Yeah, this is a QR algorithm. QR algorithm. About QR algorithm, this algorithm, the matrix A can be any matrix. Now, consider one special case. Okay, a special case. Special case. When A is symmetric, this case, symmetric. From linear algebra, we know that any symmetric matrix can be factored as A. Q is a orthogonal matrix. We can find for a symmetric matrix, we can find an orthogonal matrix and diagonal matrix lambda, diagonal matrix, such that A is equal to Q lambda Q transpose. Q transpose because Q is orthogonal. Orthogonal means Q times Q transpose is I. So Q inverse is Q transpose. So actually, this is a when A is symmetric theoretically, A can be factored as sum of orthogonal matrices. These orthogonal matrices is columns, eigenvectors of the matrix A, and lambda diagonal matrix. The diagonal entries of lambda is eigenvalues of the matrix A. Then for this special case, AK in the QR algorithm, when apply the QR algorithm to a symmetric matrix, then the AK will approach an upper triangular matrix. Now, because upper triangular matrix now is symmetric, so this matrix is diagonal. It can be proved AK actually approaches lambda. Yeah. Then which matrix in the QR algorithm will approach this Q? Yeah. If we let S be, let me see. Okay. When K is 0, we have Q0. When K is 1, we have Q1. And so on. Let's compute the multiplication of Q0 to QK. Then I use SK to denote the product. Then it can be proved SK will approach Q, approach this Q. This Q, the columns are eigenvectors. So in this special case, QR algorithm, the iterate AK will approach a diagonal matrix consisting of eigenvalues. And if we form SK to be the product of Q0, Q1 to QK, then SK will approach Q consisting of eigenvectors of the matrix A. Yeah, let me also show one example about the symmetric case, about the take a look at second example. Yeah. Example 2. Consider this matrix. Now, this matrix is a symmetric matrix. 2. Yeah. 1, 3, -1. Symmetric. Symmetric means the transpose of matrix A is equal to the matrix itself. Then perform QR algorithm. Perform QR algorithm on this matrix A. How many iterations? After 20 iterations. After 20 iterations, then what we have, we have A20. Then factor QR factor on A20. We get Q20, R20. Then Q20 is this matrix. Identity matrix. After 20 iterations, then Q20 is identity matrix. And R20 is this matrix 6.32, 34.000. 3.3579. It is an upper triangular, but almost diagonal. Yeah, this matrix upper triangular, but almost diagonal. Okay. Yeah. If this entry is 0, then diagonal. But this entry now very small, so almost diagonal. After 20 iterations, we get this, and also we get S20. By definition, it is a Q0, Q1 times Q20. This S is 0.0710. $5.90. Yeah. Okay, now iteration number 21. A21 is R20 times Q20. Yeah. R almost diagonal. This matrix times Q1. We get because round of error. It turns out that $87, yeah, 87. I don't know, maybe due to round of error, this Q20 not exactly identity matrix. So R20 times Q20 becomes looks like exactly diagonal matrix. And S20 is S21 is S20 times Q20, right? Q21 times Q21. But here, according to my notes, I didn't QR factorize Q21, so A21, so I don't have Q21. Okay, after 21 iterations, now A21 is a diagonal matrix. So these three numbers are the eigenvalues of the original matrix. And and I can use S20. The columns are the corresponding eigenvectors. So this is a special case for the QR algorithm. Yeah, when A is symmetric, the iterates converge a diagonal matrix of eigenvalues. This is topic one. Topic one. Second topic, some improvements. In practice, QR algorithm, this algorithm actually has many problems. Say, for example, in each iteration, we need to perform QR fertilizations. But this step very expensive in computational cost. The floating point operations to perform a QR fertilization is order n cube, order n cube. When n is large, this step very time consuming. Very time consuming. Now, is there any idea or any method to reduce the computational cost of QR algorithm? Let me show you two examples. Okay. Yeah. Okay. The first example. Example 1. How to make improvement. Okay. Consider the case when A is symmetric. When A is symmetric, we usually find an orthogonal matrix. Before I perform QR algorithm on the matrix A, we first find an orthogonal matrix. Let me give a name. Say U. U is orthogonal. Yeah, that means that U transpose times U is I, identity matrix. Find an orthogonal matrix such that A is simplify the matrix A. No, such that U transpose times A times U is a tri-diagonal matrix first. Okay, this is a tri-diagonal. Tri-diagonal, that means that the matrix has only 3 diagonal lines. Yeah. Yeah. Tri-diagonal. Yeah. All other entries are zeros. This is tri-diagonal. Okay. Before we perform QR algorithm on A, we first transform A into a tri-diagonal matrix. Then perform QR algorithm on T. Yeah, because T is similar to the matrix A. So T and A, they have the same eigenvalues. So I can perform QR. I can look for eigenvalues of T, right? The eigenvalues of T, they are the same with the eigenvalues of A. Okay, now this is an improved algorithm. Okay. We call this algorithm the symmetric QR algorithm. Step 1. Transform the matrix A, the symmetric matrix A, into a tri-diagonal matrix. Then set T0 to be T. That means that I want to perform the QR algorithm on T rather than on A. Step 2, perform the for loop K from 0, 1, 2, and so on until convergence. Until convergence. Okay, now TK. In step K, perform QR fertilization on QK. Yeah. And then the last step, multiply QK and RK in reverse order to form TK plus 1. Okay, then and the follow. It is interesting when T is a tridiagonal matrix. Perform QR factorization on T, then arrow times this arrow times this Q. The new matrix still tridiagonal. So the new T is tridiagonal. Then the next step, the next K, perform QR factorization on this new K. And then arrow times Q. Again, we have a new tridiagonal matrix. To perform QR factorization on a tridiagonal matrix, the floating point operation is that floating point operations roughly is order n. Roughly is order n. So it is a huge save of the computational effort, right? The original A, or original matrix A, QR factorization is order n-cube. Now, perform QR factorization on tridiagonal matrix, computational cost is only order n. This is a huge save. This actually is an algorithm for the solution of symmetric matrix. This algorithm is a practical algorithm, actually. Yeah, people use this algorithm when the matrix A is symmetric. The second case, how about general matrix? How to improve the computational cost for a general matrix? Second example. Example 2. Okay, A now is a general matrix. Still, there is a way to improve the computational cost. Find an orthogonal matrix. Orthogonal matrix. How about I still use U? Okay, U. Okay. Such that U transpose times A times U. Because A now a general, not symmetric. The resulting matrix is an upper Herzenberg matrix. Upper Herzenberg matrix has this structure. Okay. Yeah. How about let me assume 5 by 5 case. Okay. Upper Herzenberg. Yeah, here. Yeah. This is a upper triangular part. The entries can be any number. Now, this line is the lower subdiagonal line. The lower subdiagonal line still non-zero, but below the lower subdiagonal line, all the entries are zeros. Yeah, a matrix of this form is called upper Herzenberg matrix. And let me show you one concrete example. Say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0, 11, 12, 13, 14, 0, 0, 15, 16, 17, 0, 0, 0, 18, 19. Yeah. this matrix is an upper Heisenberg matrix. Below the lower subdiagonal line, yeah, this line is called subdiagonal line. Lower subdiagonal, upper subdiagonal is this line. Okay, below this line, all the entries are zeros. A matrix of this form is an upper Heisenberg matrix. Before I perform QR algorithm on the matrix A, first transform A into an upper Heisenberg matrix. Now, this matrix has the same eigenvalues with the original matrix A because symmetric. Yeah, a Q is orthogonal. Then perform QR algorithm on H. Yeah, so the algorithm is also this version of QR algorithm. It is a practical version. Okay. The name for this algorithm is the unsymmetric QR algorithm. Step one, transform the matrix A. Find some orthogonal matrix. Transform the matrix A into upper Heisenberg. Now set H0 to be H. Then perform for loop until convergence until convergence. Okay. Now HK in the cave iteration, we have HK. Perform QR factorization on HK. This step, if here is the original matrix AK, then this step is the floating point operations. The number of floating point operations is about NQ. Now, because H has special structure, now this step, the floating point operations is about N squared. Okay, one order reduced. After we get factorization on HK, now form new H. New H, yeah, and then the for loop, yeah. This version is a practical version and much faster than the basic version of QR algorithm. Yeah, yeah. Here are two improvements. Yeah, this is all about eigenvalue problem, all about finding eigenvalues. Next, let's turn to a new topic about the solution of linear systems. As I mentioned, in numerical linear algebras, two main topics, two main research areas. One is finding eigenvalues of a matrix. The other one is solve linear systems. Okay, now this is topic 3 from section 4. Iterative solution of linear systems. Linear systems. Okay. Topic 3. Now this time, let's consider linear systems. consider AX is equal to B. A is a real matrix, n by n. Usually n is very large. Of course, B is a vector. Here, we assume A is large. How large? Usually, it doesn't like eigenvalue problems. An eigenvalue problem, the matrix A usually million or more, but here billion. Okay, the size. Large and sparse. Sparse means most entries of the matrix A are zeros. So to store a sparse matrix, we only need to store non-zero entries. We don't store zeros. So the storage of a sparse matrix actually is cheap, not expensive. Okay. All right. From linear algebra, we learned that a typical solution method for a linear system is Gaussian elimination, right? Gaussian elimination. The first method, okay, is Gaussian elimination. But in practice, when coefficient matrix is large and sparse, Gaussian elimination is not a choice for solving the linear system. Why Gaussian elimination is not a choice? The reason is, okay, take a review. What is Gaussian elimination? In matrix language, Gaussian elimination GE consists of two steps. Step one, perform LU factorization. Factorization on the matrix A. In more general, perform PLU factorization. That means that perform P. P is a permutation matrix. What means permutation matrix? A matrix obtained by interchange the rows of identity matrix. The matrix is called a permutation matrix. Find a permutation matrix P such that P times A is equal to L lower triangular matrix times the upper triangular matrix here. L lower triangular. Yeah, the matrix L lower triangular. Okay. U upper triangular. U upper triangular. Yeah. GE. The first step about GE in matrix language. Okay. Is find a permutation matrix, find a lower triangular matrix and an upper triangular matrix, so that we have this equation. Now solve the linear system. Then A is equal to B. From this equation, we have multiply P to the both sides. Then by this equation, P times A is L times U. Then set U times X to be 1. Therefore, to obtain the solution X, we first solve Ly is equal to PB. Because L is a lower triangular, solve this linear system, we use forward substitution, right? Forward substitution. The computational cost is order n squared to get y. Okay. After we solve this equation for y, then solve ux is equal to 1 to get x. Because u now upper triangular, perform backward substitution to get x. Yeah, this is a Gaussian elimination, 2 steps in matrix language. Okay, it doesn't like the solution of a linear system in linear algebra. In linear algebra, how we solve the linear system? Form augmented matrix, then perform elimination to transform the augmented matrix into epsilon form, right? Then perform backward substitution. Yeah, that is the elimination language. But in matrix language, perform LU factorization, then solve these 2 triangular linear systems. Actually, the same thing. Okay. Then what is the problem with Gaussian elimination? The problem is, even if A is sparse, a sparse matrix, the storage requirement is very light, right? We only store non-zero entries. Okay. Even if A is sparse, but L and U are usually dense, not sparse. Dense means most of the entries non-zero. But we have to keep L and U in order to solve this linear system and this linear system, right? But to keep L and U, the computer need to be able to store how many non-zero numbers and square so many non-zero numbers, because when L is full, U is full or dense, then together how many non-zero entries and square non-zero entries. So in order to perform Gaussian elimination, your computer should be able to store and square so many non-zero entries. But this storage requirement is huge, especially when n is a billion, say for example. So yeah, this is a difficult storage problem. Because of the storage problem, people usually don't choose Gaussian elimination to solve a large and fast linear system. Then what method people usually choose? Iterative method. Okay, iterative method usually requires much less storage to perform than Gaussian elimination. Yeah. So in topic 3, in section 9.3, okay, we introduce some well-known iterative methods. Okay, yeah, but those methods are but those iterative methods in section 9.4 actually they are very old. Okay, they have a history of 100 years. Okay, yeah, long time ago. But they are still in use in some computational areas. Say, for example, in multi-grid methods, we use part of the multi-grid method, lead iterative methods in this section 9.4. But yeah, they are still in use, but not popular. The most popular today, nowadays, about iterative method, they are named Krylov subspace methods. Yeah. Krylov subspace methods are most popular nowadays. Okay. But anyway, in section 4, we study iterative methods, even though they are very old, but they are still in use today. Okay, in some areas. Let me stop here. Yeah, and on Wednesday I present those methods.